Welcome to Chapter 4, Atoms and Elements. Section 4.1, Elements and Symbols. Elements are pure substance, as we learned in Chapter 3. Symbols are used to identify the elements. It is either one or two letters that are used to abbreviate the names of the elements. In the symbol for an element, if it's only one letter, the first letter is always capital. So if it's the first letter or the only letter, it's always capital. If there is a second letter, it's always lowercase. Okay. Now, there is a periodic table that I have uploaded. This one right here, okay? You can print this out for your own use to, it's the same one that I would give out in a physical classroom. I would give it out on blue paper like I have it here and like I have it posted in Canvas. Your textbook also, the front cover, or maybe it's the first page depending upon your version, okay? The periodic table right here. So when you look at the periodic table, you see symbols, either one capital letter or one capital and one lowercase letter. Okay. So these symbols come from the current name or the Latin, Greek, or German name. Some of the symbols are pretty obvious. H for hydrogen, N for nitrogen, O for oxygen. Okay, some of them are pretty straightforward. Some of them, PB, plubis, for lead. The term plumbing comes from the Latin word plubis because pipes were originally done with lead. So plubis, Latin for lead. Fe, ferrous, for iron. Okay. Hg is the symbol for mercury, from the Latin hydrogurum, literally meaning water silver, because mercury looks like liquid silver. Its nickname is quicksilver also because it's this silvery liquid. W is the symbol for tungsten, from the German wolfram. And there's a lot. There's a lot of other ones. Na is for sodium, comes from the Latin natrium. Okay. Gold is Au from Aurelia. Ag is silver from argentium. And I could go on and on and on about where some of these origins come from. The initial pages of the textbook, as I already said, give you a periodic table, but also give you, right across from it, you have your periodic table, and then you have the names and symbols of all the elements opposite that, okay? Now, if you look at the periodic table, I believe it was 2015 or 2016, all of the elements were officially named. International Union of Pure and Applied Chemists, these were all named. So if you're looking at a periodic table and these are not filled in with symbols, it's because it's an older periodic table. I will write that down for you, what the names and symbols are of the newest named elements. The new element names, some of them are listed in the textbook, some are not. Just to be complete, element number 112 is Copernicum, symbol Cn. Element number 113 is Nihonium, 115 Moscovium, 117 Tennessine, 118 Oganesson. And they are named, these last four are named after the respective universities or cities where they were created. Okay, these are artificial elements created under extreme conditions and in reality only existing for probably a few seconds or minutes. Copernicum, named after astronomer Copernicus. Okay. The periodic table is so interesting. I have videos that I'm going to include, well, I will have them included in Canvas. You know, we could spend a lot of time talking about the periodic table. It's so interesting to learn about it. but just the layout of it. Let's talk about the layout of the periodic table. Okay, so section 4.2, the periodic table. Let's talk about the layout. Horizontal rows are called periods, and the vertical columns are called groups. Sometimes they're called families. Okay, so the horizontal rows, horizontal across, okay, these are called the periods, and it's labeled periods in your inner, in the cover of the inside of your textbook. Vertical columns are called groups, and you can see it's listed with the group numbers, okay? Some textbooks call them families. Groups is the more common word. The A group elements collectively are called the representative elements. So, and the heading is the same on the blue chart that I gave you too, the blue periodic table. 1A, 2A, oh, sorry. Show here, it's easier to hold up. 3A, 4A, 5A, 6A, 7A, 8A. These are your representative elements or main group elements. In the middle here, the B groups are your transition metals or transition elements. Try to use the textbook one again. The textbook has them labeled. Okay, transition elements right there in the middle. The B groups. The lanthanides and actinides down here at the bottom, okay, are called the inner transition or rare earth metals. And a lot of these were discovered in the 30s and the 40s, and when they were discovered, really weren't sure what they could be used for. At the time, they really didn't have much use when they were discovered. As time went on, some of those elements were used in production of televisions. Now, the rare earth elements, a lot of them are used in manufacture of smartphones, how we get the different colors in the display of a smartphone. So, even though right now these elements, we don't really know what use they're going to have, who's to say that 50, 60, 70 plus years from now, they may have a use, just like the lanthanides and actinides when were first discovered, didn't have a use, and now they have a very important use. Okay. Some of the A group elements have special names, special classification. The elements in group 1A are the alkali metals, with the exception of hydrogen. Hydrogen is not a metal. Okay, so you have alkali metals in group 1A. In group 2A, you have the alkaline earth metals. Group 7A, you have the halogens. And a lot of your halogens are used in disinfectant products, chlorine, bromine, iodine. Okay. Group 8A are your noble gases, which are sometimes referred to as inert gases because they don't react with anything. Now, under extreme conditions, xenon can be forced to bond with a halogen. Extreme conditions, for only like a few seconds or a few minutes, just enough to, make a point about it. But the noble gases, inert gases, don't react with anything in their standard conditions, and pretty much even extreme conditions in general, they don't react. So noble, not doing anything, inert, okay? So these groups have special names, okay? Yes, all the A groups are main group elements, representative elements, but these ones have a special additional classification. And your periodic table in your textbook does have that written across the top. You have this stair step dividing metals from non-metals. And it's easy to see on a color-coded periodic table, like the one in your book. The one in your book is color-coded. And you see the bold stair step here. But you may not always have a color-coded periodic table. Okay, and I have this one here posted for you in Canvas. And I bolded the line, the stair step just to make it clear for the video. But you can see it if you choose to print out that periodic table. You may not have a periodic table that is color coded. So this staircase here is important to differentiate the metals from the non-metals. And then it identifies those elements which are called metalloids. Metalloids have properties of both metals and non-metals. And to be specific, these are the elements that are metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and acetine. The newly discovered or newly named elements we don't know enough about yet to categorize as a metalloid or a non-metal. So we're going to leave those ones off the list for now. Okay, and for the sake of clarity, we're going to go with the ones that are the traditional ones here. Okay, so you may say, well, what are the properties of metals and non-metals? All right, well, let's talk about what properties are for metals and what properties are for non-metals. Okay, I'm going to show that in a moment. But I do want to bring to your attention, and I do have this also in Canvas. Okay, this is a graphic periodic table. So Theodore Gray has collected samples of elements. And if he could not find a sample of the element itself, he found a compound that was made up with that element to show a picture. Now, you're going to see this video as well in higher resolution than me holding this chart up. But you probably can see from viewing this where you're at. Do you see how many of these elements are metals? Now, you all know what a metal is before even coming into chemistry. There are so many elements that are metals versus the ones that are non-metals. Okay? So we have many elements that are metals versus those that are non-metals. Let's talk about what the properties are of metals, non-metals, and metalloids. Metals. Metals have properties of being shiny, ductile, malleable, and good conductors of heat and electricity. Now, you may be looking at some of those words and not quite sure what they mean. Well, I think we all know when we say that a metal is shiny, I think we know what the property of being shiny means. Ductile means that it can be drawn into wires, such as I have copper wire. Can be drawn into wires. Okay. Malleable, meaning that it can be hammered into sheets or foil, such as the aluminum foil, okay, or the gold foil that I have here. So malleable can be hammered into sheets. Just like you have that bone in your ear called the malleus, okay, I might be saying it wrong, which is shaped like a little hammer. So malleable can be hammered into sheets. And metals conduct heat and electricity. On the periodic table, the metals are to the left of the stair step. They are to the left. In the color-coded one, they are listed as blue. Okay, so all of your metals are to the left of the staircase with the exception of hydrogen. Hydrogen is a non-metal. All of your lanthanides and actinides, okay, they come out of the periodic table right here. They are all metals. Okay, so if you're looking at a periodic table that is not color-coded, again, all of your metals are here, okay, with the exception of hydrogen, and all of your lanthanides and actinides are metals as well. Non-metals, on the other hand, are dull, non-ductile, you cannot put them into wires, non-malleable, you cannot hammer them into sheets, you do not conduct heat and electricity. I have here 2 samples of sulfur. Could you imagine putting this into a wire? It would break apart. Same thing here. Could you imagine putting that into hammer that into a sheet? No, it would fall apart. Okay. Metals do not conduct heat or electricity. And the metals, I'm sorry, the non-metals. Non-metals do not conduct heat and electricity. And the non-metals are located to the right of the staircase. Also hydrogen as well, okay? Now something that is a metalloid, like silicon. Silicon is a metalloid, okay? And the metalloids are right along the staircase. I'm going to write that as well, okay? The metalloids have properties of both nonmetals and metals. Silicon is used a lot in electronic applications because it conducts electricity very well, but it does not conduct heat. So silicon is a prime material to use for electronics. Okay, just to reiterate some important things here, hydrogen is a non-metal, despite it being listed on the left side of the periodic table, along with all of the other metals. It is a non-metal. Hydrogen is a gas. We'll learn a little bit later on why it is listed where it is listed. Aluminum is a metal, despite it being along the staircase along with metalloids. When we define the metalloids, okay, they're either above or below the staircase, and I had written in the previous, a few minutes ago in the video, exactly what the metalloids were. And I did not include aluminum on there because aluminum is considered to be a metal, okay, even though it is along the staircase with the metalloids. Aluminum is a metal, hydrogen is a non-metal. And then do not forget that the lanthanides and actinides, which are down here at the bottom, are metals. When you look at any periodic table, there's usually some notation. Your textbook and the chart that I have here, you have an asterisk for the lanthanides and you have a cross for the actinides, and you can look where they reference in the periodic table, okay, the asterisk and the cross there, okay, showing that these come from here, okay, they are metals. The color-coded chart shows that as well, but if you did not have a color-coded chart, that doesn't prevent you from identifying them correctly. Okay. So there's some really cool videos that I have in a Word document, because I have them compiled in a list, that go into more detail about the periodic table. So I would advise that you would look at the videos that I have in that document after I do the next section called the atom. Okay, I'll place it in Canvas in that order. So you watch my video first and then the other videos that I have collected over time and have shown in class that are good to explain some more details with the periodic table and the concept of the atom, which is where we're going next, the atom. The atom. The atom is the smallest particle of an element. So when we look at the periodic table and we look at all of the elements that have their symbols listed, all of those elements are made up of atoms. Okay, hydrogen is made up of hydrogen atom. Sodium is made up of sodium atoms, okay? It's the smallest particle of an element. Over time, many theories have been developed to describe the atom. And your textbook goes into some background information about some of those older theories that are not the current accepted theory. And feel free to read about those. J.J. Thomson's model, plum pudding model, Dalton's atomic theory, okay, Rutherford's model. Look through those in the textbook just to get some background information. If you're going to take Chem 121, you talk about them in a little bit more detail, because atomic theory is done in more depth in that course. So you could just read through them if you would like to. But we're going to talk. We're going to go right into the current accepted theory, which is the nuclear model of the atom. The nuclear model of the atom contains subatomic particles, which are electrons, protons, and neutrons. We're going to look at a diagram of the nuclear model of the atom. and we're going to talk about each of these 3 subatomic particles that make up the atom. Okay. Now, we cannot see atoms with our individual eyes, but with the aid of a scanning electron microscope, we can see atoms. And I have a video called the Atom Movie that is included in the list of videos that I'm going to put after this video. You'll see it in Canvas as a Word document with about 5 or so videos in there. You'll see one video entitled the Atom Movie, where you can actually see the results from the scanning electron microscope, where they actually move individual atoms around. It's quite impressive. All right, let's look at a diagram of the nuclear model of the atom and the subatomic particles that comprise the atom. Okay, so let's talk about the nuclear model of the atom. We think of something as having a nucleus, and maybe you've learned in biology the term nucleus as it relates to cell structure. The nuclear model of the atom, you have the centralized nucleus. The nucleus contains the subatomic particles of the protons and the neutrons. Okay, so however many protons or neutrons that element has, however many of those subatomic particles are concentrated in the nucleus, the protons and the neutrons. Protons have a symbol P with a superscript of a plus. Neutrons have a symbol N with a superscript of a 0. Okay, lowercase p, lowercase n. Outside the nucleus, you have the electrons. Okay, so they're in a region outside of the nucleus. And the electrons have a symbol lowercase e, superscript minus. Okay. The protons have a positive charge. The neutrons have no charge. They're neutral. Okay. Electrons have a negative charge. Okay. When you think of electricity, electricity is the flow of electrons. Okay, you have a flow of negative electrical charge here. Okay, from one area to another. Okay. So protons, positive charge, symbol P plus. Neutrons, no charge. Okay, neutral, 0 charge, N, superscript 0. Electrons, negative charge. Okay. E, superscript negative. Now, in the video that I will show after this, or that I referenced, the Atom Movie, you can see individual atoms with the aid of a scanning electron microscope. Okay. But the subatomic particles are too small to see individually. Look at the masses of the protons, neutrons, and electrons. Protons and neutrons have similar mass, with the neutrons slightly a little bit more. Okay, you can tell by the coefficient from the number in scientific notation. So see why we use scientific notation? Look how small that number is. Could you imagine putting 23 zeros in front of that 1? All right, that's a lot to write. So we use the scientific notation. 1.673 times 10 to the negative 24th grams is the estimated mass of one proton. One neutron, roughly the same, on the order of 10 to the negative 24th. Electrons have even a lower mass, 9.11 times 10 to the negative 28th grams. So electrons even have a lower mass than the neutrons and the protons. Okay, so collectively, these particles make up, these subatomic particles make up the atom. And then the atoms make up elements. Well, in the next video, we're going to talk a little bit more about the periodic table and the information that we can get from the periodic table. We can get a fair amount of information from the periodic table as it relates to atomic structure.